what we now think of physics, the universe, the protons, the neutrons, the electrons, the Big Bang, space and time. In fancy words, we call it the noumena. That is what really exists in naturalism. That is what science studies. But what we see, as in visual illusions, is not that. What you see, as I showed you last time, is widely different from physics. So that we usually call phenomena. And we do understand that the link somehow happens in our brains, because certain brain lesions cause you to be blind. Taking certain substances changes the way that you see. So the question is then, how do we get all of this together? And obviously that is a very ancient question. Now, last time I gave you a proposal, and the proposal was that the answer lies in science being about laws of nature. Usually we debate in science until we reach that level, that we have a law of nature or an equation, and that's usually where debate ceases. Less people interested debating E equals mc squared than Darwin's theory of evolution. And I told you that actually we reached that point more than 100 years ago, thanks to this scientist, Gustav Fechner, and he gave us an equation that allows us to take stimulus quantities, physical quantities, and I showed you numerosity or density or weight, and with this function you can translate that and predict how people perceive these quantities. So that's good science. That's a law of nature stating that your perception is logarithmic, and I invite you to verify it yourself. You can, after class, walk outside of this building and look up the building. If there's more and more floors, they seem to be more and more squished together because of that logarithm. This law of psychophysics governs your whole perception, and it's good to know because it distorts the way that you see reality. Now, I don't want to go too far down this rabbit hole, even though it's very interesting, because I still owe you this. I have to tell you mathematically how we go from this physics, not directly to perception, but what is the brain doing in all of this? And of course, my stance is this should be mathematical as well. Now, this question, for the longest time, remained unanswered. So meet Francis Crick, co-discoverer of the double helix structure of DNA, and Christoph Koch. Francis unfortunately passed away a couple of years ago. Christoph is still very much with us. Francis used the prestige and influence that came with getting the Nobel Prize for what arguably was the secret of life. Let me remind you, before we understood the double helix structure of DNA, we had no clue how inheritance works. We knew that DNA has 4 base parts, A, T, G, and C. But how does that give some people blue eyes and other people brown eyes? Once we understood the double helix structure, it all became clear. And the notion that we cannot explain life based on physics, which held up until this point a notion called vitalism, it went away. In fact, you probably never heard about it. That's how much it got demolished. So Francis, he felt motivated that maybe he can solve that other problem about conscious, subjective, visual perception as well. And they had a genius idea. It is one of the few papers that I'm aware of that was ever published in Nature. And remember, that's the most prestigious journal that we have in the entire universe. That was just a question. And what they said is what I just told you before, that we have the noumena, the physical world, the universe, reality, nature. We have the brain, that's part of that. And then we have what we all know are neural processes. These cells in your brain that we learned are discrete, exchange chemicals and electrical signal, and that is it. So when I'm talking about you seeing the color red as red and blue as blue and feeling love as love and hate as hate, how does this work? And they said, in order to do good science, we need good experiments where we hold everything constant and we change one thing. And at a fundamental insight. The insight is already apparent to you because I showed you visual illusions. And they do not correspond to the world. You did not see the lines in the middle of the streets change when I did it right in front of your eyes, repeatedly so. So what that suggests is there must be 2 brain processes, 2 types of neurons, if you will, in your brain. One that registers, that gets the information about the world. It sees that there's 2 different images that I'm showing you, and then a second set of neurons, and they did not correspond to what the actual images were. They corresponded to your perception. So Christoph and Francis, they suggested that we have, in fact, most of our brain activity this unconscious, indeed, computational process. That is what most of the brain is doing, because your body has to control where the blood pressure is, how regulated, how your body temperature is regulated, how much sugar you allow into the bloodstream, go to these different organs, and luckily you don't have to be aware of it. The second part, which is whatever this neuronal activity is doing that makes it conscious. It links it to your conscious perception. So they called it back then the NCC, the neural correlate of consciousness, because we want to be careful that really what we can observe is just correlation. So we call it a correlate. We just see that these neurons, they correlate with your conscious perceptual states. Okay, let me show you that this really works. I'm going to take some information that your body is processing right now. It's fully available to you, but it remains fully unconscious. And just using my words, I'm going to make it part of these neurons that you're conscious of. Can you feel your clothes? Can you feel your clothes right now? Now you do. That information was present the whole time, but it wasn't in your conscious awareness. And just by saying it, you realized my body has that information, and yes, I can feel my clothes. As I keep talking, 5 minutes from now, they will go back right into the state and you will forget about what your clothes feel like. Now, the actual experiments that Francis and Christoph suggested, I was enamored by the idea. It was the following. This is my favorite visual illusion. So if you put your eyes right there on the dot in the lower part, if you want to be contrarian, you can pick a different dot. But don't move your eyes. So if you do not move your eyes, of course, you will see what I'm showing you. There's 3 red dots and a cloud of black dots swirling around them. But there you go. The other red dots disappear. Now, if you move your eyes again, you can see that we're always present. So the physical world, nature, reality, again, is unchanging right here, but your perception is zoning in and out. You're seeing these red stimuli, yes or no. The idea is the following. So if we have a stimulus that is constant, in other words, unchanging as a function of time, it goes on, it stays on until we turn it off. But your consciousness, your perception, your vision is going between I see the red dot and I don't see it. I see the red dot and I don't see it. As long as you look, it will randomly go between these two states. We can now look at your brain activity, and we should find 2 types of brain activity. One brain activity, the one that we call unconscious, the sensation, it should reflect unchanging inputs to the eye. Truthful, veridical neural processing. Well, and then we also should find this. If you believe that there's a link between brain activity and your conscious perception, what you see, you should find some neurons do something, go up and down in activity, synchrony, whatever you think it is, but they should change in something that goes exactly in lockstep with what you're seeing, a correlate of consciousness, if you will. Now, this idea, again, was just proposed in Nature. People ran back to their labs and said, let's study that. There is a whole group of people that have done exactly these experiments, very carefully and rigorously so. And you can see, again, Nature right there, Science, Nature Neuroscience, Nature Neuroscience, Nature Neuroscience. These were high-impact publications at the time. They were done using fMRI, using electrodes. And I do not want to give you all of the details right there, because you understand what I just said. What these studies did is they showed that some neural activity seems to go in lockstep with what you see and what you don't see, and other activity doesn't. I will show you next a patient that was treated for severe epilepsy. That's a lethal disorder if you cannot get it on a medication, because these people, just imagine if they drive a car, get an epileptic seizure and they hit yours. So we do surgeries with these people, but at the same time, if your brain is linked to you, your love, your hate, you're seeing the color of red, we don't want to cut out too much brain. So what we do is we put electrodes in these people, and then we wait for the seizure to happen to find exactly the small part of brain that we want to cut out. And so here's a patient, and to keep the patient anonymous, you will not actually hear the patient. There will be a robotic voice once the patient speaks, but you can hear the neuron. And as you know, a neuron gets electrically active for only 1 millisecond and then goes back to rest. So what that actually sounds like, if you listen to it, is a crackle. So we can listen to these neurons crackle, and then we can see what the patient is seeing. Let me take a quick break. So what you witness is a patient sitting in a hospital room, and you can listen to the neuron in its brain. It seemed that neuron gets very active whenever the patient sees The Simpsons. So that's interesting. Do we have Simpsons neurons? Is it that we recognize The Simpsons because some neurons become active? Well, how about this? We ask the patient what they saw. That tells you that, of course, if I find neurons that perfectly correlate with your conscious experience, that I can start mind reading, that I can predict even before you say something what you might be seeing. So that research was groundbreaking, and there were many, many publications published after that initial paper came out by Francis and Christoph, using this term, neurocorrelates of consciousness. And I'm showing you right here towards the 2000s. And then this happened. Why did these people, including me, by the way, stop doing this kind of research? Well, I'm going to argue the problem is that I just showed you half. I showed you now how stimuli relate to brain activity, but I still fail to explain you mathematically how I get from this brain activity to perception. All I said, it correlates. Correlation can't be it. What we really want is a law of nature. These handful of equations, Maxwell's, Newton's, Schrödinger's, and Einstein's, they allow us to do everything that you're doing in modern life, including using your laptop, Wi-Fi, and GPS. Well, my point is that, again, if you look at physics, from classical mechanics to relativity and quantum theory, everything is mathematically formalized. That is why we recognize that as a gold standard of science. But when it comes to the theories of consciousness, of which there are many, almost none of them are mathematically formalized. One of them is, though. And I will start talking about this theory. We can go from understanding how a stimulus evokes neural activity to how this neural activity, with mathematical laws, I have to show you some kind of transformation where I give it neural activity and I can tell what you are consciously perceiving, and that theory is integrated information theory. And it's pretty much the only theory, at least that I'm aware of, that does it. So these are publications in Nature. Can scientists ever agree? Consciousness theory slammed as neuroscience, and that theory is integrated information theory. Now, the first thing I want to say is that it is very important to understand that while we usually believe that science rests on theory and data, that we have ideas and that we test them with observation, that is very true, the debate is also a very important pillar of making sure you're not making any mistakes. And debate among scientists is not something hostile or something I'll welcome. In fact, many of the people that are part of this move to say that integrated information theory, pseudoscience, are very good friends of mine and continue to do so. We see this as positive, not as negative. And the other thing is that my friends and I that are on two opposite sides on this debate, we all agree on a whole lot. In fact, there's so many things that we agree on that I probably bet that there are some things in there that you might disagree with all of us. But for example, we do agree that you have to use experiments to decide which theory is correct. We do agree that believing that everything is consciousness is meaningless. All agree on. We only disagree on very little. What is that, though? So I want to make next a very, very strong case that I believe has been built against integrated information theory. So the claim is, and I'm of course paraphrasing here, but again, see if you agree with me that this is strong. The first claim is that science cannot prove theories, but it can disprove or falsify theories. So what defines science is that you have to be able to disprove a theory. Why can't you prove something? Well, the famous example is that we believe that all swans are white, and by we, I mean people back in Europe at the time, until they went to Australia and they found a black swan. So they were wrong. So future data can always disprove you. But once you find a black swan, the assumption that all swans are white has been disproven once and for all. So new data can change our understanding, but it does seem to do it asymmetrically in that we can rule things out. So one black swan rules out all white swans, but even if we only see white swans, that doesn't mean that there are only white swans. So now the next one is that you cannot use the measure of integrated information theory that I will talk about more, called phi, on a human brain and compute its number. And there's two reasons for that, technically speaking. One is computers are struggling with that, and the other one is that, yeah, that's a lot of data. And then lastly, if we have to experimentally falsify a theory, but we cannot compute this number, we cannot falsify one of the most important parts, and I will call it a core assumption of the theory. We cannot disprove it because we cannot compute this number. And so it follows then, if this is defying science and we cannot falsify a core assumption right there, that integrated information theory is pseudoscience. It's not real science. The logic is sound. You cannot attack the logic. What you have to do is you have to question the assumptions, and that's what I want to do next. So let's take the assumption that you have to falsify in science. So that is the criterion how we tell science from pseudoscience. That seems very strong, but the problem is, wait a minute, that goes both ways. Falsified theories actually sometimes get unfalsified. Why? Because we got more data. Let me give you some examples to make that more concrete. Einstein, in 1917, introduced in his theory of relativity something that we call the cosmological constant, or lambda. Now, in 1929, Einstein was still alive. He met with Hubble, who, of course, gave us the Big Bang Theory by showing everything moves away from us. And the further it is away from us, the more there's a redshift, the faster it moves. That doesn't go with this. This does the opposite. So Einstein himself called it my biggest blunder. Well, the issue is that once we got more data, in 1998, we started introducing dark energy, which is exactly the cosmological constant. So while this seemed to falsify that, more data showed us that no, indeed, the initial assumption was incorrect. So yes, of course, it is true that when I get more data, I learn more, and I might be proven wrong, but I might even be proven wrong when I said something is wrong. It doesn't seem to be a good criterion. So this is Karl Popper, who came up with this idea. Science cannot prove anything, science falsifies. I'm going to show you the original attack on IIT and just going to give you a quote. This is a quote from this original attack that 100 scientists signed. If IIT is either proven, if IIT is proven, say the people that say science can't prove anything. So there you see that this is very confusing. Okay, so there's already one problem. Okay, so, but what about we cannot compute phi for now? So we do not have all of the data of your brain, and we do not have computers that can do it. The Higgs boson was proposed 48 years before we could build the Large Hadron Collider in Switzerland. It was science all along, and then eventually we could do it. So this doesn't seem to be a hard argument either, because we will get there. Maybe, maybe not. This is just a temporary embarrassment, not a real fundamental problem. And here's the other one. You cannot falsify the core of this theory, and so hence there's a problem. Now I'm going to tell you that is also a misunderstanding, at least in my view. The Big Bang is fundamentally unobservable. We will never see it. It lies behind what we call an observational horizon set by quantum physics. Macroevolution will never be observed by humans. It takes millions of years. Quantum superposition is fundamentally unobservable. The observation itself destroys superposition. We cannot test the core of these theories because they're fundamentally unobservable. Science doesn't test the assumptions of theories. It tests the consequences. We call it a prediction. Now, what about integrated information theory? So I don't have enough time to fully introduce it, but I will tell you, here are its core claims. And I would just lie out a few of them. That a system has cause effect over itself. This is something that in IIT is called intrinsicality, has a specific state with a specific cause and effect. We call it information, and that it is irreducible. Now, these are core assumptions that, if you will, we can test directly because they give us predictions. They say that if these things aren't met, you do not have consciousness. Well, are there parts of the brain where they aren't met? Yes. So the cerebellum, for example, is not conscious. And if you ask why, most theories will not give you a very straight answer, but IIT is telling you it's because of this. When this isn't met, there is no consciousness, and the anatomy of the cerebellum doesn't meet it. Now, it's not just anatomy, it's also the state of the neurons. For example, what I said right here. My point is that the conclusion, while it is logically sound, it's still invalid because all of the assumptions at closer inspection fall apart. Okay, so if you're interested in all of this, then I will point you to these publications in Nature Neuroscience, where the original case is presented, a response is presented, and then also an attempt at a compromise. If these logical arguments don't really hold so much water, the question is, maybe there's something more going on. What might it be? And so I'm going to propose, and I don't want to go too deep right here, into this idea by Peter Kreeft, that classical philosophy and modern philosophy are a little bit at odds. And that classical philosophy, and I'm talking about Aristotle, Plato, antiquity, was very much focused on realism, the substance, the essence, the logic, the being, the state, the perfect, the absolute, rigor and laws and objectivity, whereas modernity has shifted towards how things are, relations, interactions, experience. Becoming is more important than being. Complexity, more interesting than simplicity. Flexibility, maybe more important than laws. You find that these two things seem to clash in psychology and philosophy. And so I'm going to use Martin Buber Beaumont right here, where he said, maybe this is more of a view of the I embedded in the world, whereas this might be the world embedded in the I. And you can maybe already think that, yeah, this maybe resonates more with me, or this resonates more with me, and how this affects our thinking. Now, I'm going to say this, what I said last time, that this is more about what is, about the state, the being, the essence. And I said that you can use it with this logical or semantic term of extensional, where this is more about how things come about, the becoming, the process, the experience that's involved. And again, also, of course, your first order perspective. And so just to really briefly show you what IIT is, it really is just mathematics. So what we'll have to do is we have to measure neurons, we have to see their states, and then using this mathematics, we come up with geometry. We're building a topological construct, and this construct is what we think in explanatory value explains your consciousness. So you can see what IIT actually does. It provides you both. It provides you on this level, a how level, in terms of like this, what is happening in the brain, the causal interactions between neurons. But then it also provides you what things are. And to just show you how this mathematical formalism works, I told you before that if you are in dreamless sleep or in the cerebellum, you do not have these rich conscious experiences, and that falls out of the mathematics. So it's not just words or concepts. We can actually do the math and come up with that. So I'm going to argue that IIT bridges both sides, the existence, the universal, the laws, the realism, the objectivity, the mathematics, but also your intrinsic subjectivity, the phenomenology, the process. And hence, it finds no friends on either side. It's attacked from both sides because it's in its own unique camp. And I'm going to argue for the last couple of slides that it's not really IIT that's doing that, it's mathematics that does that. Mathematics explains both these sides, states and process. So real brief, IIT, like all mathematics, starts out with axioms. We have to make some assumptions. IIT has 5. And axioms should be statements that you find very convincing just by itself. So what IIT says is, think yourself away, question everything. Well, you can't question yourself away, can you? So it starts out with this point of like, I can be so doubtful, but that doesn't go, my consciousness doesn't go away. And it says, okay, then what does consciousness feel like? What does it have? Well, it seems to be intrinsic, it seems to have information, and so on. So based on these axioms, then IIT comes up with mathematical properties. It says, well, if consciousness, your vision, has information, we have to come up with a mathematical definition of information. Those of you that are interested and want to go down a rabbit hole, there's ways of learning the mathematics of IIT. There's this wiki. This is the mathematics of IIT. It's about 20 or so equations. It's all written down in Python code. So if you're interested in it, you can go in 10 minutes and explore IIT. And people do. So for example, here's one of the studies I found the most interesting published in the last couple of years, where people did neuronal activity measurements in fruit flies. With these new electrodes that we have, where you can measure hundreds of neurons at a time. They run it through integrated information theory, and then they do compute that number that I mentioned before, phi, that we cannot compute for the human brain. And you see that if these fruit flies are awake or anesthetized, just as the theory predicts, that number is higher or lower. But how can I tell you what you actually see? And I told you that in the end, what IIT does, it gives you a topological structure. Technically speaking, it's a graph. It's a higher order graph. It's what we call a hypergraph. But how can a graph explain what you see? How can this right here be the color red, the color blue, or love or hate? So this is where I want to introduce you to the idea of an isomorphism. So when it comes to music, Western music, you might have learned that there's something interesting. If I go up an octave, the tone is definitely higher in pitch. But at the same time, if I go up exactly 1 octave, that tone is more similar to the original tone. That's what I'm showing you right here. If I take the note C, that C is more similar than the other notes. It's also higher up. Now, if I ask people to tell me how similar are things, they will, in a 3D space, put these notes in a helical structure, into a helix, because the distance now between C and C is less than between the other points, and yet it is higher up in pitch. Now, I could also use 3D color space or other ways of geometry that you're already familiar with that are taking your perception and mathematizing them, formalizing them. So all that we're saying in IIT is that we will come up with mathematical structures that will be isomorphic, that means in the same structural configuration, structurally identical to what you're already describing in your perception. That is obviously true for the color circle, where we go in different hues in a circle, and then from complete darkness to complete brightness, up and down. It is true for the musical helix. It's also true for faces, by the way. So this was a discovery by one of my PhD advisors, that if you take any faces and you see how people faces, in fact, you can even find neurons, you orient them in a space. Now, the people that are interested in IIT, they take it a step further. They're showing you that if the brain is what it is, based on the anatomy that we know, and we're using that mathematics on, let's say, the auditory cortex or the visual cortex, it explains to you why space feels the way that space does, and why sound feels the way that sound does. Lastly, each time that science starts to make that huge leap, that we start having laws of nature, mathematics, often things fall out of it that are useful for society as a whole. I'm going to point out this paper that makes another very interesting point. In the abstract, they say there's a widespread assumption in neuroscience that once all neurons have been caused to fire or not to fire, it seems that causally there's nothing left to be accounted for. And you might intuitively agree. Now, this is mathematics in this paper, and what they show is that this is implicit, unexamined. Nobody has ever shown that. And what it actually does, it conflates causation with prediction. So while that is true for prediction, that may not be true for causation. Once we have a causal calculus, a mathematics of causation, then we can come up with explicit operational approaches, mathematical approaches, able to put numbers on causation. And so IIT has been instrumental in that. And then lastly, I made this point last time, IIT tells us that ChatGPT, no, it does not feel love the way that you do, because after all, it is just software. By the way, I'm not arguing that it is impossible to build synthetic artificial consciousness, but it will not be the case with a von Neumann machine. Long story short, I believe that IIT is the missing piece. Do I believe it is correct? Do I believe it's all we need? Of course not. It's a first step. It's the first theory that we have that's mathematically formalized and where we can go and test these things the way that I showed you. In fact, the people that do IIT, they know that, and they change the theory every couple of years based on these insights. We're on round 4. So IIT 4.0 is the current version of IIT. We know it's work under progress, but it does give us this. It does take away that we had before, that we thought naturalism can only explain physics and your consciousness is somehow not part of nature, of science. No, it is very much part of science. It is mathematics. We can look at the brain, we can study it. And as I said last time, it seems to take away the magic between neural activity and consciousness and replaces it with mathematics, which of course is the only thing you can have in science in the first place. Consciousness first.